have Aki Vehtari describing the Agile Probabilistic AI program of the Center for AI and also some related research, I hope. Welcome, Aki.
Thank you. Good morning, everyone. For the first slide, I'll put here then this kind of the overall the goals of FCAI, and so I'll come back kind of to how this program then contributes to achieving data efficiency, understandability, and trust, and of course that we can also talk about a bit of ethics. So if I open kind of these three things in the title, here the artificial intelligence is considered in a wide sense, including overall machine learning, statistical models, and I guess you know kind of the most used AI probably is logistic regression, invented already in the first half of 20th century, which could be also then just called as a statistical model. But of course, we have a kind of the thinking about the wide range of different things, and in different contexts we might use then these different descriptions for these statistical models, ML or AI. Probabilistic, so that uncertainties are quantified with probabilities, and inference is based on probability theory. And it is important then that we have these probabilities describing the uncertainty, so that when we are making decisions, we can properly take into account uncertainty, what might happen if we make certain decisions. Agile refers here particularly using probabilistic programming ideas and then having automated inference. And also now, specifically, very important part of this program, and which is kind of the more of this new research, is then the software-assisted workflow, how we can help the user more than what's been currently available with these probabilistic programming automated inference approaches. So now one example to make it a bit concrete, some of these things I then discuss. This is time series analysis, fitting a model to time series and then making predictions. The specific time series is STAN is a probabilistic programming framework. RSTAN is R interface for that. These are RSTAN downloads from RStudio, Cran, Mirror. But this could be time series for customer, number of customers visiting a store, demand of some product, server load, electricity demand, and so on. And these kind of time series can be quite complex. You can see the black dots are now the observed number of downloads. There's the blue line fitted to the data, and I'll zoom a bit further. And there's also now, you can see end of the that there's also prediction to the future, and that prediction also includes uncertainty. If we think about product demand or how many customer service people we might need certain day electricity demand, it's important that we take into account also this uncertainty and kind of what is the cost that, what if we run out of the products, or there's long queues in store, or there's not enough electricity. You can also see in this that the kind of the pattern is complex, and we've been able to find out certain structure there. You can see these shorter kind of the periodic jumping pattern, bit of otherwise kind of following the data up and down, and then some spikes. And we can then break this in parts. Here in top, we have overall trend during the years. We can see that the number of downloads is increasing. We jump to the third line. We have weekly pattern. So during the weekend, Saturday, Sunday, there's less downloads. And there's a yearly pattern, which you can see reflects quite well the academic year. So there's less downloads during the Christmas break and during the summer, and more downloads when the teaching is going on. We have also then the second line, which has a title holidays, these spikes. For this data, they are actually these release dates when new Arstan release was made. Kind of a holiday for Stan developers, of course. And overall, you can see that we were able to include a lot of useful structural information. We did not need to learn from the data that there's a 7-day period called week. We did not need to learn from data that there's 365-day period called year. We could include these kind of structural information there. And also we could include what are the specific dates when there was a release. And if we make predictions in future, and if we know that, okay, this date is going to be release date, we can include that. In the same way, if we think about customer flows, electricity demand, we, for example, can use the information when is Easter. If you try to find out what's the rule for the placement of Easter, you need quite many years of data. It's quite complicated. And even because kind of there's a strange difference between actual astronomy and certain simplified model for astronomy, there are some of kind of rare occasions where there can be even compared to real astronomy, 30-day difference where Easter is located. So it's very complicated. But instead, we can include all these domain knowledge easily. And we can make these models modular, that we can see how these different parts contribute to this time series. So in this triangle in the beginning, I had this data efficiency, understandability, and trust. So we can improve better data efficiency by including domain knowledge. You could see in the previous example, including the information about calendar and release dates helps a lot. We can also get better data efficiency by integrating over uncertainties using Bayesian inference. This is something that, especially when we get more and more complex models, more and more unknown parameters, it's been shown in many examples that we get more accurate predictions and more reliable predictions when we do this integration over the uncertainties instead of, for example, just optimizing maximum likelihood. Understandability, one part is that we should use modular models. It's not just the kind of the breaking time series in smaller parts. Any information we include is likely that we can include it as subpart. And this would be also go for deep learning models. they are also often constructed so that they are modular. Different parts are contributing certain thing in these deep learning models, especially in the kind of the more advanced ones specified for the certain task. One thing when we are using these probabilistic programming approaches and certain workflow principles, we can combine model building with the process to understand the phenomenon, so that we start with a simple model, which is easy to understand. We add something simple to that, which is again easy to understand the chains, and we add something which is easy to understand the chains, and that way it's not just that in the end, when we have very elaborate model, it should be something that is easy to understand, but it's also possible that by having the human build this model themselves, they are actually then learning more and they can understand this better. And when they are building it piece by piece and they understand it better, hopefully they can also then explain the end result better for the others, but they can also show kind of the simpler parts also when explaining that, look, this would happen if we start with the simpler and go to more complex. Important part is these what-if questions, that when we have the final model, we can ask that what if Easter would be tomorrow? What would then happen? And kind of able to simulate from the model potential future and compare then to that kind of the additional external knowledge we did not yet include, or we did not know yet well how to formulate that in mathematical form, because with the computers we need to always, any knowledge we have, need to formulate in mathematical form to get the computer to understand, but we often can make that kind of what-if questions and then compare, does this reflect what we otherwise know? Trust, big part of that comes, of course, from understandability. It's easier to trust something we understand. One part of the trust is that we keep human in control. We know that computers and computer software often has bugs, and very complex systems have sometimes strange behavior. But more we include human in this process, more trust there is, of course, if we trust that human. So it starts from that part also. We can use a lot of diagnostics. So we let the human be in the control, but have automated diagnostics as much as possible, checking that, okay, what the human is doing, does it make sense? All the automated inference, is it working for the specific model? Because it's really difficult to make anything automated which would work always. And then, again, these diagnostics should be such that human would understand then possibilities how to go forward, how to fix the model, how to fix the inference, and so on. Trustworthy software. For all of these, we need software, and we need to trust that people who are making this software are really interested in that it's reliable, that they have a lot of tests for all parts, that they are all the time using the best possible diagnostics, best possible inference algorithms, that they are using good software development practices, good release practices, so that they are not hurrying to release new software release which might then have a bug in some algorithm and produce really strange results. So there's a lot of going on that we trust the software we use. Another example of this kind of the using a lot of domain knowledge, achieving data efficiency. So this is example for estimating drug dosage, correct drug dosage. And this is the everolimus, is an immunosuppressant which is used after organ transplants. And in this case specifically the data is from liver transplants. And so after we put the new liver in human, the human body notices that this is not original liver, it's a foreign object. Immunosystem tries to reject it, and immunosuppressant then cools down the immune system not to fight too much. But at the same time, we don't want to shut down the immune system completely, so we don't want to give too much of this drug. So we want to be in certain range. So one part of the problem is to find out how we can control that the concentration in the interesting part stays in certain range. And of course then the other part would be that what is the certain range that will keep most of these patients alive, and so that the liver is not rejected. The human body is very complex. When the patient gets a drug, for example orally, it's a very complex process if we would start from first principles, that how are these molecular reactions going on in stomach and how the drug then diffuses the blood and transformed by blood and so on. But it turns out that at the same time, even if this is very complex, it can be modeled with quite simple model. So there's these pharmacokinetic models. So there's a gut where, so the orally, the drug goes there. It diffuses from there with certain speed to blood and tissues. And then from blood and tissues, it then diffuses to this peripheral compartment. So tissues, kind of what's the interesting part also, where the drug should have an effect. The speed, how fast the drug goes there, depends of course how much drug there is here, but also how much there is here. And then again it diffuses faster when there's no drug there. And then eventually kidney removes this drug from the body, and then the concentration starts to drop, and eventually then again concentration starts to drop also over there. And we can get this, you see the black line describing the concentration. You can see it starts very low, so the initial dosage, and then the red circles are the new dosages and also the measurement point. And it's interesting that this simple model having only these 3 parameters for the speed of the kind of the modeling the dynamics, and then there's a parameter how the body weight, so the body volume affects these, and we can get accurate estimate also for the highest concentration, even, and so that we don't need to measure that anymore. Of course, in the initial experiments when validating these models, they measured more, but now we need to only measure the concentration when we are also giving the new dosage. And so this was also now learning then from the data how the body weight affects this. And then it is possible to make these drug tests also with healthy adults, just testing how the concentration behaves. and possible to fit a model with 500 adults. But we are not allowed to make these tests with children. So how we can then find out how to use this for children? We have the model which includes weight, and we could then think that, okay, let's extrapolate based on the weight. But children are not just small adults. And for example, here the kidney, it matters not just based on the weight, but also age. So it's typical that the young children, the kidney is not as efficient removing this drug from the body. And this is called maturation effect, and it's likely that these younger children, they would need smaller dosage because kidney is not removing this as fast. So we can start with this model, taking into account the weight, include now then also the age, and then we know that this maturation effect is very likely to be such that if there would be no maturation effect, it's just the adult model. But with the maturation effect, the effect is such that it goes monotonically down, and it's always then below the adult model. And including also, and otherwise we don't know what is the form, but we can again add this model to this. And it was enough to have observations from 17 children, which is not much, but combining with the adult information, this gives useful information that for the future. And so this from the observations come now from the actual cases where there was need to make a liver transplant for these children, and then the drug was used anyway, and then eventually these are not common cases, but even with the rare cases, we eventually get some information, able to learn the maturation effect, and then safer to use for the future. Again, we have different models and are able to go to add kind of additional part. And here again, the probabilistic programming helps, that we are able to build these models piece by piece, or when we add new component, we can have the automatic inference doing the inference again without that we would need to start to think that, okay, how do we solve the inference problem now? And so probabilistic programming, it's not a new thing in a way that there's been like the bugs for Bayesian probabilistic programming already started in end of 1980s. I'm part of the STAN development group, but there are also others like PyMC, Pyro, TensorFlow, probabilities with Edward layer, and few others, which all have the kind of the benefits that there's something which is specific for building certain kind of models. And these different frameworks also have different flavors. Some of them are more towards deep learning models and more towards certain approximative inference. STAN is more on Markov chain Monte Carlo and more about the trying to do the Bayesian inference as accurately as possible. Having the kind of specialized language makes it faster than to write models, and having kind of the certain model components already part of the language or extended language. Automated inference, that in most of the cases should be just that after you've written your model, you just say that, okay, make the inference and that's it. Although now some of these frameworks also then are part of the language is then also used to describe how to make the inference also, so that it's possible then to kind of tune the inference for certain models. Of course, it then requires additional work, but that's also in some frameworks possible. All these frameworks have some of the diagnostics, although then part of the frameworks have also made it externalize that so that there are separate packages then having these diagnostics for checking inference and checking kind of the model checking. So that was kind of the big part of that was, of course, what's already there, and of course we are working to improve all these parts. A lot of this kind of the ideas of that we have this iterative model building is also, for example, Box wrote about that in 1980s, Rubin, also 1980s, Rubin, Gelman, 1990s, and a lot of people are kind of presenting about these ideas that we have this iterative model building that makes some model, check that easy if it's good, and or find what is the kind of the where it fails and how to improve it. But then that's only one part of this modeling process, and there are also many of these other parts discussed, but currently there's not so much with kind of the literature or software which would try to handle all of this. Starting from pre-data, what we know about the phenomenon beforehand, can we do some prior elicitation and prior structure elicitation, design of experiments, that we would actually do better experiments, which is kind of more likely to answer our questions. The modeling part, being iterative, we have some baseline models. Also in deep learning, it is recommended that you should also have the logistic regression as a baseline. Have a ladder of models, kind of not just have the baseline and then the most complex, but go bit by bit more complex. When we are using probabilistic programming, we come with the kind of what are the programming practices, good programming practices, design patterns. So there's a lot of ideas we can use just from software development literature and good programming practices literature. For the inference, algorithm choice, model parameterizations, diagnostics, there's a lot of things to choose. Some of these can be made very automated, but there are always some cases that something automated doesn't work right away. And then we need diagnostic which says for the user that, okay, now you need to investigate your model or your inference a bit more, and here are how you can do it, and depending what is the answer from these diagnostics, you could do this or this or this. Model checking, same way. What is how we can give advice how to change the model if we see certain model checking diagnostic results. Finally, we are happy with our model. We want to make predictions, decisions. Of course, these utilities, losses in decisions might affect also how we make the inference. And then we have all these things, and we should be able to guide the user through all these parts. And all the time, it would not be just that go read this book, go read these 10 books, go look this case study vignette in internet, but how we can do it in software-assisted way so that the software understands how this workflow, all various different paths we might go depending on what the different diagnostics say, And at the same time, it's not just that the user would be blindly following what the software says, because if they are blindly following, then we could do this also just automated. But all the time, trying to also educate the user. So if the user has some basic understanding of the modeling, and they've been able previously to make very simple models, when they start making more complex models, they might encounter new problems, and then the software assistant would tell them that, okay, now there's a new problem you haven't encountered before. Now we recommend reading this material and then using these commands to diagnose and then go forward based on what you learned. And we come to that, we are actually also then have this interaction where we are educating also our users, which will come to back that by that the user doesn't need to know everything beforehand, but they will learn, and that learning will make them more an expert, and that will also then increase trust. So they should be all the time understanding why the machine recommended certain diagnostics, why in these different choices, why now the human decided to do something. But we come then also in the end, we have the reproducibility. Because now the workflow had these different possibilities, different branches that different users might actually make different choices in different parts. Especially when the users don't know a lot, it's more likely that just by chance what they've learned affects what kind of model they use, or do they ignore some diagnostics. So they might end up going very true path when doing the modeling. But if we have the software assistant, we should have more stability how different users are going through this path. But also, the software assistant should make it so that there should be more consideration in important branches, bringing more stability. It's also that we can all kind of record that there were the branches where the user made this choice, but we can actually then check that what if the user would have made the other choice, and check what would have been the result. And we can check, is the result similar or much different? So we can also look at what is the stability. And we have both the stability kind of that sometimes some choices might depend on small changes in data. Maybe there's just one additional strange observation in one data. It might affect how the user goes through this path. We want that it would be stable. If we could kind of at the same time in a parallel universes have the user analyzing slightly different data, we would like that they would come up with the same conclusions, similar predictions and similar decisions. And also, if we have the same data but different users, we would like that in the end they would come up with the similar predictions and decisions. Or we could diagnose that, okay, now there's a problem, this is very unstable data or model, and now we should do actually kind of multiverse analysis. We should actually kind of think that what combine possible different paths. So we are building these better tools, and then this program is strongly connected to also these FCAI Interactive AI Modeling Made Easy programs. In some parts, we need to think that what's the kind of this interaction between human and machine, that there's kind of there's no feedback loop where we would somehow passing the same information in a loop and kind of making that certain information look more bigger than it is. that we need to think about these possible feedback loops. And of course then different user interfaces. There's one prototype for what this could look. I hope they are in future a bit more even better, and when this has a lot, it needs also already, or at least it should be kind of probably again showing bit by bit this information. Graphical user interfaces are really big challenge, how we can balance again showing something clearly, not too much, but able to go deeper and deeper for those who can understand more. Okay, that's it.
Any questions, Joaquin? Self-explanatory, apparently.
Who would you say are the target audiences for this package?
So we have different target audiences. So we start with the more of experts that who are already experienced and currently kind of the so specifically I'm working on STAN and probabilistic modeling for Bayesian models, but kind of the ideas we are developing are transferable to also these deep learning frameworks, how to build deep learning models. And even if it's not probabilistic deep learning models, there are a lot of these workflow ideas which are also then transferable there. But kind of where we start is now the experts Bayesian data analysis people that how we can make these some of the repeated tasks easier in a way that it's kind of that if you do a repeated tasks, you might at some point kind of get bored and try to skip some of the parts, but how we can make it easier that they will follow and don't miss anything. But and then we are going for the kind of the not that expert people, and then eventually kind of the beginners, where they maybe, and so one of the goals is even that we can use this in teaching, that we can have just maybe half-day introduction, and then already say that, okay, now start making just simple generalized linear models with our tools. Next day, having another half day of bit more, and then, okay, now you can go to hierarchical models, and again using our tools, and so that they are able to use their own data sets, and we don't need to worry that what if their data set is something which causes certain problems, because this will then guide them that, okay, now you need to do this, and now you need to read this, and so on. When they and they can continue, and we can have these kind of online courses where people are using these tools to learn also all parts of the workflow, and also there's also that the kind of we want to cover the whole workflow, but at the same time we are of course building sub-flows, and then it means that expert users are likely to use sometimes only subflow parts. The complete workflow is easiest to make when we also know that there are certain restricted set of models. But then expert users will make very complex models, and then some of the part of the software assistant is then, it's very difficult to make it for open-ended models, but still the subflows for inference diagnostics and model checking, they can use those parts. And then, as I said, eventually, of course, we think that like even if we are starting from like generalized linear models, hierarchical generalized linear models, GAMs, any Stan model you can come up with, and then eventually also these deep learning models and so on, that we could get these workflow ideas, software assisted workflow ideas there.
Very quickly, I'm looking for Gaussian versus models with gradients.
Mm-hmm.
Does this package have such facilities?
So not yet. But of course, that's also these models are kind of thing we are interested in, and would kind of, as I said, there are different levels. Some of these flow software would recognize that certain models, also Gaussian processes, and could help with specifically with them. But then part of the subflows can be used even before we have a specific support for Gaussian processes. You can use the other subflow parts for the generic diagnostics.
Just a thought, I guess one part of this project is to provide some informed recommendations for the model for the user.
Mm-hmm.
Could you kind of use it for providing some kind of auto-ML kind of yes, or so provide some kind of first step at the model kind of automatically without any kind of user intervention?
So some of these things going behind are a bit like AutoML, but in a way, the AutoML advertises clearly itself as that it's automated, that user doesn't need to do anything. In the end, you will get automated report, and the best model has been selected. And yes, we can do behind, like I talked about multiverse analysis. We can do that behind, and then it has wider resemblance with AutoML. But we want to still advertise this as that human is doing this step by step, having the ladder of models, learning about going from simpler to more complex.
Yeah, that makes sense. There's just the idea that there actually could be a lot of benefit from providing a bit of dynamicity where the kind of user can decide the kind of level of his kind of interference with the system and kind of choose whether he will go with default or whether model needs adjustments. And I guess this is what AutoML can provide, and I think this is very kind of interesting.
Yeah. But the reason why I don't use AutoML term is that because AutoML, what is the kind of the hype advertisement there is opposite what we want to do, even if we are using very similar approaches under.
Thanks.
Would you say the status of this project? Where it is now?
So there are different things. So we are already, and we have been working with different parts of the workflow, different diagnostics. So a lot of the kind of the important subparts of the whole system. We have already, for the overall workflow, we have already some existing literature articles and books, and we are also writing new books on these, but we don't have yet that kind of thing. None of these try to tackle the very, very big complete workflow. We have already prototype for this software assisted workflow for generalized linear models going on, so that we are prototyping in the kind of the text-based interface, which gives recommendations. What is the next step in the workflow? And then we have some kind of again, because we are working together with these other programs, so with the interactive AI, so there are also some prototypes of these user interfaces which are using part of these workflow ideas and tools and diagnostics under, and kind of trying to also figure out in a way how we can go from this text-based, which yes produces also images, to more graphical user interface. That it can, because then knowing that kind of what would be requirements of the graphical user interface can affect also what we do in the underlying framework.
As you've described, different groups working on different subsections of the overall workflow. It's modeling, user interface, diagnostics, and I guess it looks like JavaScript. We've remarked about R, stands backend being C++. How does, I guess, FCAI and their collaborators manage this potentially very complex sort of language dependencies between someone wrote the interactive model in C# and JavaScript, and that needs to be able to connect up to the inputs for RSTAN, and whether you need stuff with WebML or text scraping with regards to data input, any protocols with regards to gluing all of this together. Because I can imagine it being a rather tricky task to set the entire workflow, particularly since it's independent projects rather than a single monolithic block.
Well, it's kind of that we know there are challenges, but at this point there's kind of because all what we have currently or what we are planning are prototypes.
Yeah.
So we are not yet that worried how the final product could be, but it's also that because all what we do is open, we are of course hoping that others who are not kind of in the project would anyway copy these ideas to any software. So there can be also kind of we would be lucky if someone else would actually want to do all these things.
Right.
And of course we assume that what we are going to do is that useful, that even if we would do the first prototypes, eventually others will copy these.